Hey AP, in this video we are going to look at doing calculations to plot a titration curve. So we talked about titration curves in the last video. In a titration curve we said looks something like this, where we have our titrant and we know the titrant's volume that's being added, and then we measure the pH. And if I am, in this case, we are putting in different amounts of sodium hydroxide added to 50 milliliters of 0.2 molar nitric acid. So we're starting at an acidic pH, and we're going to slowly increase our concentration. Then we said that our concentration spikes, our pH spikes, and then we start to level off again. So it has this standard shape, especially for strong acids and strong bases. And we know that at the point of inflection here for strong acid, strong base, this is our equivalence point. And at the equivalence point, our moles of hydrogen ions are going to equal our moles of hydroxide ions. Another point that we could easily pull off one of these graphs is our beginning, right? And here we would only have the analyte. So in our case, the thing that we're starting with, that is our analyte, would be our HNO3. And then we could also look at something called the half equivalence point, which is somewhere in this region. And at the half equivalence point, here, if I know my moles of hydrogen, they're going to be equal to half the moles of hydroxide. So I'm halfway to canceling out my moles of hydrogen with hydroxide in this situation. And then the fourth dot that we're going to look at is we're going to pick a point that's about 10 milliliters past our titrant volume. So we're going to do about 10 milliliters more of our titrant. Okay, and those are going to be our 4 points that we're going to do calculations for. And then based off those 4 points, we can sketch out our titration curve. And then eventually we'll do a lab where we'll actually then do the titration, and we'll see how accurate we are. So for this one, we are looking at the pH of the solutions at the indicated amounts A, B, C, and D, which is what we just talked about, our initial concentration before the titration, our half equivalence point, our equivalence point, and then 10 mils past our equivalence point. If I have sodium hydroxide and 50 mils of 0.2 molar nitric acid. So in this case, we've got a strong acid with a strong base. In each of these, we want to find pH. So if we want to find pH, means we need to find hydrogen ion concentration in all of our different situations. So let's start with in A. Let's get this set so y'all can see what I'm writing. We have just the initial concentration before the titration begins. So I have 50 mils of a 0.2 molar HNO3. So I need to know what's my concentration of hydrogen ions here. Well, that's just a simple stoichiometry problem. So 0.050 liters of HNO3. And I have here, my concentration is, for every 1 liter, I have 0.2 moles of HNO3. And we care about hydrogen ions. Luckily, it's a 1-to-1 ratio, but maybe it wasn't. But we can say that for every 1 mole of HNO3, I have 1 mole of hydrogen ions. So when I do that, I get 0.05 times 0.2. I guess we don't really have to do that, do we? Well, we can. We'll see that it's the same, because then we'll divide it. That's okay. 0.05 times 0.2 is 0.01. Moles of H plus, and we have a volume of our solution of 50 mils, so divided by my 0.05 liters of my solution. 0.1 divided by 0.05 gives me 0.2. So I have 0.2 molar hydrogen ions. We could also say that because this is a strong acid, that we have HNO3 is going to dissociate into its ions of hydrogen ions and nitrate ions. And if I have 0.2 molar nitric acid, that means because this is a 1-to-1 ratio, I'm also going to have 0.2 molar H+. So you could do that. You could rationalize it that way too. Regardless, my concentration of hydrogen ions is 0.2 molar. My pH is equal to the negative log of my hydrogen ions. And so that gets me a pH of 0.70. So right now, in situation A, I have 0 milliliters of sodium hydroxide added, and I have a pH equal to 0.70. So this is my first point in time of A. So this would be where I start here. Now B, we said is going to be our half equivalence point. And at the half equivalence point, I'm going to have half as many moles of OH as my moles of hydrogen ions. Okay, so I need to figure out moles of hydrogen ions that I have to start with. So like I said, if we have 0.050 liters of HNO3, for every 1 liter, I have 0.2 moles of HNO3. And for every 1 mole of HNO3, I have 1 mole of hydrogen ions. So I am starting with 0.01 moles of hydrogen ions. So I'm at the half equivalence point. That means that I am going to have half as many of my OH ions. Oops, it should be a minus. OH ions. So half of 0.01 is 0.005 moles of hydroxide ions. So if I need to have 0.005 moles of hydroxide ions, I need to know what volume of sodium hydroxide that is. And I need to know what volume of sodium hydroxide that is. And I need to figure out my concentration. So I am first going to figure out my volume. If I have 0.005 moles of hydroxide, and I know that my concentration is 0.1 moles of sodium hydroxide. Well, technically, we should say that we have, for every 1 mole of hydroxide ions, we have 1 mole of sodium hydroxide. We should be technically correct. And with my concentration, if I have 0.1 moles sodium hydroxide for every 1 liter sodium hydroxide, when I multiply this and divide, I get 0.05 liters of sodium hydroxide, which is 50 milliliters NaOH. So I know my volume of sodium hydroxide, 50 mils. NaOH, now I need to know the pH of my solution. So to do that, I need to figure out, well, how many ions are floating around in my solution of either hydrogens or hydroxide, so then I can figure out my hydrogen ion concentration and then my pH. So if we are essentially reacting hydrogen ions from our nitric acid plus hydroxide ions from our sodium hydroxide and a strong acid, strong base, so they are going to make water. That's what's happening at our half equivalence point. I said at my half equivalence point, I have 0.01 moles of hydrogen ions, and I have half as many moles of hydroxide ions, 0.005 moles of hydroxide ions. Well, these hydroxide ions are going to react with my hydrogen ions in a 1-to-1 ratio. So these are all going to get consumed by my hydrogen ions, right? Because it's 1-to-1. So I'm going to be left with no hydroxide ions and a leftover amount of 0.005 moles of hydrogen ions. And then water, we don't care about. So if I have a leftover, if I have a leftover 0.005 moles of hydrogen ions, and I want to know its concentration, that is in solution of 50 mils of sodium hydroxide, because that's how much I needed to get my 0.005 moles. And I have that in solution with my already 50 milliliters of nitric acid. That means that in total, I have 0.1 liters of solution. So when I do that math, I get 0.05 molar, which is my hydrogen ion concentration. Taking the negative log of that, I get a pH of 1.3. So my pH, 1.3. All right, so I have my 2 points now. I have at the very beginning, I have at the half equivalence point. Letter C is now at the equivalence point. And at our equivalence point, our moles of hydrogen ions equals our moles of hydroxide ions. So if we have hydrogen ions reacting with hydroxide ions to make water, and we said we're going to have equal amounts, so 0.01 moles of hydrogen ions, 0.01 moles of hydroxide ions, and then I've got water. Well, if my two are going to react together and they're at a 1-to-1 ratio, that means that they're going to change by 0.01, because that's how much I have of my least amount. I'm going to have 0 of either of my hydrogen ions or my hydroxide ions left. So if I have no hydrogen ions and no hydroxide ions, this is a completely neutral solution. And we know that a neutral solution has a pH equal to 7. So right now I know that my pH is equal to 7. What I need to know is my volume of sodium hydroxide in order to make this many moles of my solution. So if I have 0.01 moles of hydroxide, and I said for every 1 mole of hydroxide ions, I have 1 mole of sodium hydroxide, and my concentration is 0.1 moles sodium hydroxide for every 1 liter. And when I do that math, 0.01 divided by 0.1 is 0.1 liters NaOH, which is 100 milliliters NaOH. So I've got my third point, my equivalence point, 100 mils of sodium hydroxide, my pH of 7. Now I can do my final point. My final point is going 10 milliliters past my equivalence point. So that means that I'm going to have 110 milliliters sodium hydroxide. I'm going to have 110 milliliters NaOH. And I need to know, well, at that time, what is my pH going to be? Well, I need to figure out, well, how many moles of hydroxide do I have now in solution to react with my acid? So if I have 0.110 liters of sodium hydroxide, that means my concentration, 1 liter, 0.1 moles NaOH, and 1 mole NaOH, 1 mole OH ions. I do that, I get 0.011 moles of OH. So in my reaction, I have still hydrogen ions reacting with hydroxide ions, making water. If we have what do we got? 0.01 moles of hydrogen ions reacting with 0.011 moles of hydroxide ions. Well, these are going to get run out of first because I have a smaller amount. So I'm going to decrease by 0.01. So I'm going to be left with no hydrogen ions, but an excess of 0.001 moles of hydroxide ions. So if I have 0.001 moles of hydroxide ions, and the total volume of my solution at this point is my 110 mils of sodium hydroxide plus the 50 mils of nitric acid, means I have 160 mils or 0.160 liters of solution. So that makes my concentration of hydroxide ions to be 0.00625 molar. From there, I can get my POH, which is the negative log of this, which is 2.2, which means my pH is 11.8. So now I have a pH of 11.8. Now I've got 4 different points on my curve. 1, 2, 3, 4. Now I could plot my curve and draw out my titration curve. All right, so that is for a strong acid with a strong base. We didn't really have any equilibriums here, so we didn't have to worry about Ka values or anything like that. But in reality, we're probably going to do titrations where we have weak acids and strong bases, or weak bases and strong acids. So let's go through one more where we have to now think about equilibriums. All right, doing this again. So 4 points again this time, where we're going to do our initial concentration, our half equivalence point, our equivalence point, and then 10 mils beyond our equivalence point. Okay. So we are starting with 50 mils of a 0.1 molar acetic acid is getting titrated with 0.1 molar sodium hydroxide, and we're told our Ka value is 1.8 times 10 to the negative 5. So starting out, we want to know the initial concentration before anything starts. So if I have 0.05 liters of acetic acid, HC2H3O2, and I have a 0.1 molar solution, so for every 1 liter, I have 0.1 moles HC2H3O2. Oh, never mind. We can't do it that way. Just kidding. It's a weak acid. We have to figure out how much of it dissociates. We need a nice chart. That's the whole reason we're doing this. So if I have acetic acid and I only have acetic acid, HC2H3O2 is hanging out in solution. It's going to make an equilibrium with its hydrogen ions and C2H3O2 minus its acetate ions. So we are starting with a 0.1 molar solution of that. It has not dissociated yet. So minus x plus x plus x. 0.1 minus x, but that's insignificant because it's a weak acid. We're told our Ka value is 1.8 times 10 to the negative 5. We know that Ka is products over reactants raised to their coefficients. So we do that, we get x squared over 0.1. When I solve for x, I find that x equals 0.00134, and x is my hydrogen ion concentration. So this is equal to hydrogen ion concentration, because it doesn't fully dissociate. That's why we have to make our ice chart. Right? So we can make a note. We want weak acid equals ice chart. weak acid, ice chart, have to do it. So I know my hydrogen ion concentration, which means that my pH is equal to the negative log of my hydrogen ion concentration. And when I plug that in, I get a pH equal to 2.87. So far, I have 0 milliliters of my sodium hydroxide, and I have a pH equal to 2.87. So point number 1. Now let's do our half equivalent point, B. So there's a special case when we have a weak acid and a strong base, or a strong base with a weak acid, about our pH value at our half equivalence point. So for a weak acid plus a strong base, like what we have, or for a weak base plus a strong acid, at the half equivalence point, the pH is going to equal my pKa. Okay, my pH is going to equal my pKa. And we're going to prove what that is in a second. So we're starting to add our sodium hydroxide to our acetic acid. So we have a new reaction. We have our acetic acid, HC2H3O2, is reacting with the hydroxide ions from our sodium hydroxide. It's at equilibrium. And so this hydrogen is going to go to our OH. So we're going to have H2O, and we're going to have C2H3O2 minus. Okay, we are saying we're at our half equivalence point. So I am starting with, I need to figure out what, moles, right? Yeah, we want moles because we want to know our moles of hydroxide compared to moles of acid. So if I have 0.05 liters of my acid, my HC2H3O2, and I have a concentration of my solution of 0.1 moles per liter, that means that I have 0.005 moles of acetic acid, HC2H3O2. So that's how much I am starting with. So that is my moles that I'm starting with, 0.005 moles. And at the half equivalence point, I'm going to have half as many moles of hydroxide as I do with my acetic acid. So half of this is 0.0025. I don't care about water, and I haven't made any of my acetate ion yet. These are reacting in a 1-to-1 ratio, so all of my hydroxide is going to get consumed. So this goes away. So I'm left with, and this is going to get added over here. So I'm left with 0.0025 moles of my acid, no hydroxide, and 0.0025 moles of my acetate ion. We need to figure out what volume of hydroxide we need to do this. So if I know my moles of hydroxide, 0.0025 moles of hydroxide, and we know that for every, we know that we have 1 mole of hydroxide ions for every 1 mole of sodium hydroxide. And my concentration of sodium hydroxide is 0.1 moles of sodium hydroxide for every 1 liter sodium hydroxide. I'm going to have 0.025 liters NaOH, which is 25 milliliters NaOH. So that's good. So I know my volume. I've got 25 milliliters. NaOH. But now I need to know my pH. And we said that our pH is equal to our pKa. And we know that because we have this formula under equilibrium that we haven't used yet. So our pH equals pKa plus the log of H, or of A minus over HA. Okay, this we're going to use at our half equivalence point. Okay, it's a new formula. But it's a handy formula when we're dealing with weak acids and bases. So we're going to say that our pH equals our pKa plus the log of our anion, C2H3O2, over our acid, HC2H3O2. Well, these are the same number, so that means this is going to end up being 1, and the log of 1 is 0. So that means my pH equals my pKa. Well, pKa is the negative log of my Ka. So the negative log of my Ka, my 1.8 times 10 to the negative 5, gives me a pH equal to, right on my page, 4.74. So I know my pH, 4.74. Whew, that was a lot. So in summary for that step, we're at our half equivalence point. So at our half equivalence point, if I need to know my number of moles of acid I'm starting with, which we figured out based off of our volume, figure out our number of moles. Then we had to figure out if we have half equivalence points, so we have half as many moles of hydroxide as I do my hydrogen ions in my acid. All of those hydroxide ions will react with my acid ions. And so I'm left with no hydroxide ions, but I have leftover moles of acid and its conjugate base, right, because it's lost that acidic hydrogen. To figure out pH, I take my pH equals pKa plus the log of this guy over this one, which ends up being my pH equal to my pKa, which I did. And I had to figure out my volume of sodium hydroxide. To figure out my volume of sodium hydroxide, I took the moles that I needed of sodium hydroxide, and using stoichiometry and its concentration, I figured out its volume of sodium hydroxide. Okay. Now we're at our equivalence point. Okay, and at our equivalence point, my moles of hydrogen ions has to equal my moles of hydroxide ions. So here again, I have my reaction of my acetic acid reacting with my sodium hydroxide. Again, I'm making water plus my conjugate base. I'm starting with equal moles of both. So I need 0.005 moles of my acid, which is how much I'm starting with. And I'm at my equivalence point, so I need equal amount of moles of hydroxide. 0.005 moles. I don't care about water, and I don't have any moles of my acetate ions to start with. Well, these are both going to get consumed in a 1-to-1 ratio, so minus 0.005, minus 0.005, over here plus 0.005 moles. So I'm left with 0, 0, and 0.005 moles. Now the difference here is that now that I have some of my conjugate base hanging out in solution, I'm going to have a secondary reaction occur. And what happens is my conjugate base, my C2H3O2 minus, is going to interact with my water. This is a weak base. It's going to gain the hydrogen from the water to make acetic acid, HC2H3O2, and it's going to leave hydroxide ions in solution. So now if I have hydroxide in solution, that means that I have to use my Kb value. Okay, so let's see what's happening here Well, I have my 0.005 moles. I haven't made any of that yet. Minus x plus x plus x. And this is x is insignificant here, so 0.005 moles, x and x. Okay. We need to know its concentration, so we need to know our volume of solution that we have here. So it means I need to know my volume of sodium hydroxide that I added to my solution to make this happen. So if I have 0.005 moles of hydroxide ions, and we know that for every 1 mole, I've done this a million times now. What do we got? 0.1 moles. So, I have 0.05 liters sodium hydroxide, which is 50 mils, have been added. All right, so I have 50 mils of sodium hydroxide plus my original 50 mils of my acetic acid. That gives me 100 mils, so that's 0.1 liters. So 0.005 moles divided by 0.1 gives me a 0.05 molar solution here, and that's x and x. Remember that Kb is 1 times 10 to the negative 14 over the Ka value, which we know is 1.8 times 10 to the negative 5. So my Kb value is 5.56 times 10 to the negative 10. Let's solve for x. Just keep hanging out with me, guys. So we've got 5.56 times 10 to the negative 10 is equal to x squared over 0.05. When I do this, you can trust me that I get an x equal to 5.27 times 10 to the negative 6. That is my hydroxide ion concentration. We are hanging out over here. So if that's my hydroxide ion concentration, I can figure out my pOH. So we've got our hydroxide ion concentration, 5.27 times 10 to the negative 6, which means our pOH is the negative log of that, which is 5.27, which makes our pH equal to 8.72. Whew. Okay, so we have learned here that we are at our equivalence point, 50 milliliters NaOH and a pH equal to 8.72. Okay, third point done. So if we have added 50 mils of sodium hydroxide, my last point is 10 mils beyond that. So my last point is when I've added 60 mils of sodium hydroxide. Beautiful thing about the last step is we know our volume of sodium hydroxide, so we can add that over here. 60 mils NaOH. I need to figure out my pH. So I need to know moles of hydroxide that I have in my solution now. And I need to know my reaction that's happening. So let's take a look. We still got the same reaction, HC2, H3, O2. With my hydroxide ions, I am making water and C2, H3, O2 minus. Still got our 0.005 moles of acid. We need to know our moles of hydroxide if we have 60 mils of hydroxide. So 0.06 liters sodium hydroxide. 1 liter NaOH, 0.1 mole NaOH, 1 mole NaOH, 1 mole OH minus gives me 0.006 moles, OH minus, 0.006 moles. Don't care about water, got nothing here. So let's see, we are going to have all of our acetic acid get used up. And we'll still have some leftover hydroxide, which makes sense because now we're past the equivalence point. We're in basic territory. So minus 0.005, minus 0.005, plus 0.005, 0.001, and 0.005. Now, we could look at the, another reaction here of our conjugate base reacting with water, which would produce more hydroxide ions, just like how we did up here. However, this amount of hydroxide ions from our actual strong base is much more significant than adding the small amount that would come from our conjugate base making hydroxide ions with water. So we don't have to look at that. So we say that our weak base is insignificant contributor of hydroxide ions compared to our sodium hydroxide. So, which is, convenient in terms of steps that we have to do. So that means that we know that we have 0.001 moles of hydroxide ions floating around in solution. We want that in a concentration. And we've got 60 mils of sodium hydroxide plus the 50 mils of acid we started with. So that's 110 mils or 0.001 liters. So when I do that, I get 0.0091 molar of our sodium hydroxide. That's our concentration of hydroxide ions. So from there, I can get my POH, which is 2.04, and a pH, which is 11.96. So that gives me my final pH value. pH equals 11.96. And now I have my 4 points for my graph, which I could then sketch out and draw my curve, and then I would know what my titration curve would look like. So lots and lots and lots of math. I think these are these are the most involved, some of the most involved questions that we've got in AP Chem. So just work on it step by step. And as always, we'll practice a whole bunch in class tomorrow.